Section: Introduction. In this section, we discuss recent advancements in language models, LMs, that have been influenced by reasoning models. These models are trained using reinforcement learning, RL, to articulate their thought processes in natural language before providing answers. They have shown exceptional performance in complex tasks like math and programming. The typical method for training reasoning involves using a binary correctness reward, which simply checks if the model's output matches the correct answer. While this method is straightforward and effective for enhancing accuracy, it has a significant drawback. It treats confident correct answers and random guesses the same way, and it penalizes both abstaining and incorrect answers equally. This can lead to models making overconfident guesses, which reduces their reliability. Research indicates that even well-calibrated models can become overly confident after RL training, particularly reasoning models, which often show worse calibration and higher rates of incorrect outputs when trained solely on correctness. This issue is especially critical in high-stakes fields like healthcare and law, where models need to be accurate and also express uncertainty when necessary. Our paper seeks to tackle these challenges by exploring two key questions through the framework of statistical decision theory, focusing on proper scoring rules. A proper scoring rule is designed to minimize the difference between a model's confidence and the actual probability of its output being correct. We introduce a method called RLCR, which stands for Reinforcement Learning with Calibration Rewards. This approach modifies reasoning training to encourage models to consider both the correctness of their answers and their uncertainty. We train models to provide both answers and confidence scores, optimizing a combined reward function. Our findings show that RLCR effectively promotes both accuracy and calibration. The reward is maximized when models produce the most likely correct answer along with a well-calibrated probability of success. We demonstrate that this objective can be achieved using any proper scoring rule for the calibration component. While the common log likelihood loss is a proper scoring rule, it does not encourage calibration and can lead to incorrect outputs. In our experiments on factual question answering and mathematical reasoning, RLCR achieves the same accuracy as the standard method while significantly improving calibration. For instance, we reduced expected calibration error on specific datasets. When we tested these models on new tasks, the standard method worsened calibration, while RLCR improved it, outperforming both the base model and other approaches focused solely on confidence scoring. Incorporating verbalized confidence into testing methods enhances model performance, as RLCR reduces the variability in confidence scores across different reasoning paths that yield the same answer. Overall, our results indicate that existing reasoning training methods can be easily adjusted to also enhance calibration, leading to better accuracy, robustness, and scalability. Section Summary. In this section, we discuss the limitations of current reasoning models trained with reinforcement learning using binary correctness rewards, which can lead to overconfidence and poor calibration. We propose a new approach, RLCR, that incorporates proper scoring rules to optimize for both accuracy and calibrated confidence, demonstrating significant improvements in model performance and reliability across various tasks. Section: Proper Scoring Rules. In this section, we discuss proper scoring rules, which are important when we want our predictors to provide not just an answer but also a measure of confidence in that answer. A scoring rule evaluates how well a confidence estimate reflects the actual outcome. For binary outcomes, a scoring rule is a function that takes a confidence estimate and an outcome to produce a score. A scoring rule is considered proper if it encourages confidence scores that align with the true probability of the outcome. A well-known example of a proper scoring rule is the log loss, which is maximized when the confidence matches the true probability. Our approach involves training language models using reinforcement learning, where we reward both accuracy and calibration. We combine a standard correctness reward with a reward based on the Breyer score. Initially, we prompt models to generate reasoning chains that yield both answers and confidence estimates. The reward structure encourages correct answers while penalizing high-confidence incorrect answers and low-confidence correct answers. Although it may seem that this reward could lead to undesirable behavior, we find that the calibration aspect does not compromise accuracy. We establish that the expected reward is maximized when the confidence matches the true success probability. Among calibrated predictions, the expected reward is highest for the prediction with the greatest success probability. We note that we cannot simply replace the Brier score with any proper scoring rule, as some do not promote correctness. In our experiments, we aim to assess how our method, RLCR, affects the accuracy and calibration of language models in both in-domain and out-of-domain tasks. We also explore how RLCR interacts with other reasoning methods and its impact on the coherence of model predictions. For our experimental setup, we utilize the GRPO algorithm with modifications and initialize from a base model without KL regularization. We use the Quen 2.5-7b model, known for its strong performance in reinforcement learning tasks. We set specific response lengths for different tasks and enhance our reward structure to encourage proper formatting of outputs. We evaluate several methods, including the base model, RLVR with correctness rewards, and classifiers trained on model outputs. We also explore using mean-squared error for direct optimization of the Brier score and linear probes for predicting confidence scores. Our evaluation metrics include accuracy, area under the ROC curve, Brier score, and expected calibration error. We test our method on various datasets that highlight different types of uncertainty, such as incomplete evidence, overconfidence in obscure knowledge, and complex reasoning scenarios. These datasets help us capture a range of uncertainties, from ambiguous evidence to intricate reasoning challenges. Section Summary. In this section, we discuss the importance of proper scoring rules for evaluating confidence estimates in binary outcome predictions and introduce our approach to training language models using reinforcement learning that balances correctness and calibration through a reward system based on the Brier score. We outline our experimental setup, including various methods and evaluation metrics, to assess the accuracy and calibration of our models across different question-answering tasks. Section: Dataset. In this section, we utilize a modified Hotpot QA distractor dataset that includes multi-hop questions and 10 paragraphs, consisting of 2 relevant and 8 distractor paragraphs. To assess uncertainty reasoning, we adjust the dataset by removing 0, 1, or both relevant paragraphs, which creates different levels of information completeness. Each example contains 8 paragraphs, and we train on 20,000 examples, measuring correctness through exact string matches. For in-distribution performance, we observe the training curves for our models, RLCR and RLVR. Both models show a smooth increase in correctness and calibration rewards, indicating that we can enhance both accuracy and calibration together. Our results on the original Hotpot QA dataset confirm that models trained with reinforcement learning, RL, outperform standard models in multi-hop accuracy. RLCR achieves accuracy comparable to RLVR, demonstrating that adding a calibration term does not negatively impact performance. However, both the base model and RLVR exhibit high overconfidence and poor calibration. In contrast, our method and classifiers show much better calibration, with our method slightly leading. When we evaluate generalization across 6 datasets, Trivia QA, Simple QA, MATH 500, GSM 8K, Common Sense QA, and GPQA, we find that the base model's accuracy is similar to that of RL-trained models, suggesting that RL training on Hotpot QA does not improve out-of-distribution reasoning. Interestingly, RLVR actually worsens calibration compared to the base model on these tasks. On the other hand, RLCR shows significant improvements in calibration metrics while maintaining or slightly enhancing task accuracy. We believe that the better calibration generalization of RLCR may stem from several factors. Reasoning about uncertainty can enhance calibration by allowing for confidence reflection. The dynamic nature of RL training may lead to more robust learning, and using a single model for both solution generation and calibration can improve generalization. Next, we employ Big Math, a large dataset with over 250,000 math problems, focusing on those with a solve rate between 0 and 70% and numerical answers for easy verification. Our final training set includes 15,000 problems, and we assess correctness using a robust evaluation system. To improve the quality of uncertainty analyses, we introduce a lightweight supervised fine-tuning (SFT) warm-up phase before RL. We generate solutions from the base model on 500 examples and prompt another model to produce uncertainty analyses for these solutions. In our results on math benchmarks, all RL methods significantly enhance accuracy compared to the base model. The SFT plus RLCR model achieves the best calibration, slightly surpassing classifiers, while the base and RLVR models remain poorly calibrated. For out-of-distribution datasets, RLCR and RLVR show marginal accuracy improvements over the base model, but the accuracy of SFT plus RLCR drops significantly, likely due to catastrophic forgetting from the SFT warm-up. Nonetheless, SFT plus RLCR achieves the best calibration overall, and RLCR provides a better balance in out-of-distribution settings, maintaining accuracy while matching or exceeding all baselines in calibration. Finally, we explore whether the confidence scores from RLCR can be integrated into test time scaling algorithms to enhance both accuracy and calibration. We consider various methods, including selecting the response with the highest verbalized confidence and a confidence-weighted majority vote. Our findings indicate that confidence-weighted majority voting outperforms both standard majority voting and max confidence, suggesting that combining confidence with voting yields additional benefits. Overall, the accuracy improvements from these scaling algorithms are closely linked to calibration, as better calibration leads to better accuracy. Section Summary. In this section, we describe our use of a modified hot-pot QA dataset to evaluate uncertainty reasoning and calibration in multi-hop question answering, demonstrating that our RLCR model improves both accuracy and calibration compared to baseline models. We also introduce a large math dataset for training and show that our SFT plus RLCR approach achieves the best calibration, while exploring how verbalized confidence can enhance test time scaling methods for improved accuracy. Section: Calibration. In this section, we discuss calibration in our structured RLCR chain of thought (COT) approach. Our models first provide a solution, then analyze it and give a confidence score. To enhance the confidence scores for a specific answer, we sample multiple analysis COTs, each generating a verbalized confidence score. We combine these scores to create an overall confidence estimate. Our findings show that as we increase the number of samples, the Breyer score decreases, indicating that using multiple COTs improves calibration. This method is efficient since it only requires additional sampling, unlike classifiers that need extensive training. We also explore whether reasoning enhances calibration. Previous studies have indicated that COT reasoning can sometimes be unreliable, which raises questions about the usefulness of uncertainty analysis for confidence scores. To investigate this, we trained two classifiers on a modified dataset. One classifier was trained without uncertainty analysis, while the other was trained with confidence scores removed to avoid bias. Both models had similar accuracy, so any performance differences would suggest that the reasoning from our RLCR model is beneficial for calibration. We trained classifiers of different sizes and found that while larger classifiers performed similarly, smaller ones benefited more from the RLCR reasoning. Next, we examine the consistency of verbalized confidences. We expect that when generating multiple reasoning chains for the same answer, the confidence scores should be stable. Our analysis shows that most samples have low variability, indicating consistent confidence estimates. For tasks with mutually exclusive answers, we want the model's confidence scores to sum to 1. Our results show that for in-distribution data, the confidence sums are well calibrated, while for out-of-distribution data, there is some overconfidence, though our model remains closer to the ideal. Finally, we review related work on building reliable reasoning models. We highlight the importance of calibrated uncertainty, which is often compromised by standard reinforcement learning objectives. We categorize previous research into 4 areas: post hoc verbalizations, sampling-based methods, internal probing, and RL-based calibration. Each approach has its strengths and weaknesses, but many focus solely on calibration without considering task accuracy. Our proposed method aims to balance both correctness and calibration, demonstrating effectiveness across various benchmarks.